Good morning or good afternoon, depending on where you are. My name is Professor Duke Orata. We are continuing with our lectures in thermodynamics. Today I want to look at the Van Karman model for a boundary layer. Remember, we just looked at the Prandtl-Taylor modification of the Reynolds analogy for calculation in terms of the ratio of the heat transfer to the shear stress in the system. And it was a good modification, if you recall. And we remember that in that particular modification, of the Prandtl-Taylor modification, we had said that was the Prandtl modification of the Reynolds analogy we had that expression giving the ratio of the rate of heat transfer to the shear stress, and we said that was given by here 1 plus you had U US to PR minus 1. And this expression here, which we had developed for the Prandtl-Taylor modification of the Reynolds equation, we had assumed that those integrals which we had used to derive this quantity, that the lower limit of that integral expression was sigma b. So the integrals used in the derivation of the Prandtl-Taylor modification of Reynolds analogy assumed, very important note, that the lower limit of the integrals was sigma b. The lower limit of the integral was sigma b. That is the boundary layer thickness for the laminar flow. That laminar flow, the sublayer, whose thickness was sigma b, was the lowest limit for the integrals. And remember the integrals. The integrals were twofold. We had the integral where we had tau, y, eta plus v. The integral limit was that sigma b to L. Remember in our model, you had L. Don't forget our model. This y-axis, this x-axis. This was sigma t, sigma, and that was L. You have the free stream. Don't forget this. And I keep it, all this we have discussed in our earlier lectures, and so I kindly encourage you to humbly go through them. It helps build up your understanding systematically. There were two integrals, that one and the other one. Let me just write it elsewhere. The other one was the integral of minus q dy rho Cp into alpha plus V, and again from sigma B to L. And remember, alpha is the thermal diffusivity, this is eta, sorry, thermal diffusivity. Don't forget, alpha is thermal diffusivity. And what was thermal diffusivity? Alpha is equals to K over rho Cp, thermal diffusivity. And eta is the eddy diffusivity associated with the heat transfer. Associated with the heat transfer. Heat transfer. While in this particular case, this, of course, is the eddy diffusivity. For the viscous process, and this is the kinematic viscosity. So, one of the assumptions was that we took this as our lower limit. We didn't take 0 as the lower limit like it was in the Reynolds analogy. In the Prandtl-Taylor analogy, we took this thickness of the laminar sublayer sigma B as our lower limit. Now, this is partly one of the cause of those discrepancies, which is to be corrected using the von Karman's model. So in the von Karman's model, the fundamental assumptions are that we have actually not 2 layers, like we talked of the laminar flow sublayer, and then we talked of the turbulent regions. That's the laminar region and the turbulent region. No. Now we have a 3rd layer in play. That is what we call the buffer layer. So we have 3 layers, 3 boundary layers. So we have the laminar, then we have what we call the buffer region. And then, of course, we have the turbulent region. Now, in this model, in the buffer region, it is assumed that the alpha, that is the thermal diffusivity, the kinematic viscosity, and the eddy diffusivities are all equal. In the buffer region, it is assumed that alpha is equals to V and is equals to eta in the magnitudes. And so, let us look at what kind of profile we get. So we have in our profile, so let us take a case where we have the Prandtl numbers. Remember, for example, when the Prandtl number is high, when Prandtl number, PR, Prandtl's number, PR is lying between 0.5 to 2. That's relatively high. For example, this you could find in viscous oil. You can find that in viscous oil. Or where Prandtl number is very small. For example, when Prandtl number is about in the range of 0.01, range of 0.01. This you can see in the case of liquid metals. We have discussed liquid metals also in one of the lectures, and I encourage you just have a look at it, so that if you have not looked at it already, just have a look at it and see what we mean by that. So, what happens when we have very high values and when we have very low values? Then, what do we get as our profile? So in the case, let us take a case of Prandtl number being equal to 1.00. Now, when we have the Prandtl number as 1.00, then you know already from our lectures that the velocity profile and the temperature profile will be the same. One case of Prandtl number being 1, the velocity and temperature profiles will be the same. That you already know from earlier lectures. And in fact, what are we saying? Psi will be 1 over Prandtl number raised to power 1/3, and that is sigma over sigma t. So when Prandtl number is 1, then this quantity, when Prandtl number is equals to 1, then sigma will be equal to sigma t. That we already know. That the thickness of those two boundaries will be the same. And even when you look at the parabolic solutions which you came up with to characterize the velocity and temperature profiles, they look alike. Even the parabolic expression for temperature and velocity profiles are the same. Same. What does that mean? Remember, we saw that is US, U over US was equals to 3 over 2 y over sigma minus a half y over sigma the power 3. That's for velocity. And for temperature, it was the same. It is again 3 over 2 y over sigma t minus a half y over sigma t3. Remember, sigma is the thickness of the velocity profile, boundary layer, and sigma t is the thickness of the temperature boundary layer, and they are similar. So if you profile it based on the von Karman's model, where we have the buffer layer, what you expect is, so based on von Karman's model, when PR is equals to 1, okay, so von Karman's model, when PR is equals to 1, for PR is equals to 1.00, we will have, we consider that a flat plate, and we will have the temperature. This is sigma will be equal to sigma t, and the temperature and velocity profiles are the same. But this is the laminar sublayer, this is the buffer, and this is the turbulent region. They will be the same for PR is equals to 1.00. And of course, PR is the Prandtl number. Now, when PR is large, what happens? For large Prandtl number. Now, what is Prandtl number? We have already said Prandtl number, PR, is UCP over K. And so when Prandtl number is large, and that's the expression for Prandtl number, remember that is the dynamic viscosity that is the isobaric heat capacity, that is the thermoconductivity, isobaric heat capacity. So when Prandtl number is very large, then you know that you are dividing by a smaller number. So K is small. So for large Prandtl number implies that K is small. Just let's write implies, so I've just put the sign. But that is implies that K is small. So thermoconductivity is small. So the profile which you get, so if you look at the profile for P large, PR large, the profile which you will get will be thermoconductivity being small means that, in fact, the velocity profile, the sigma T, actually is almost either equal to sigma B, that is for the laminar sublayer, or it's even smaller than sigma B. So for the temperature, so this temperature, sigma T, is almost approximately equal to sigma B. That's the thickness of the laminar sublayer. Sigma T is the thickness of the temperature. So this is the temperature profile. And this is the velocity profile. The regions remain the same. That is the laminar region. This is the buffer region. And this is the turbulent regions. And when we are dealing, so here we have said K is very small. What about when K is small, so Prandtl number is large? What about when the Prandtl number is small? Is small. So again, what does that mean? It means that from the Prandtl expression, K will be very large. So K will be large. That's the thermoconductivity will be large. And what's the import of that? Remember alpha, let's recall that alpha, like we have said, is K over rho Cp. And so basically, this K is very large, and that is rho Cp. So that in that integral, remember in the integral, we're talking where we have this quantity to L, and we had Q minus Q over rho Cp alpha plus eta. This quantity now, this quantity for alpha here, this quantity here, we have said that when PR is small, K will be very large. This K will be very large. So this alpha rho Cp, remember if you open that, we'll have alpha sigma b into L minus Q over alpha Cp plus rho Cp eta. And of course, that's the eddy diffusivity related to the heat transfer. So we are saying this quantity is very large. Large. So if it is very large, then it means that, therefore, or let me not write those three dots, you confuse people. Normally, I denote therefore as those three dots, but I will do that for now. That means, therefore, that rho Cp alpha is greater than rho Cp eta. Rho Cp eta. And so when you plot this particular quantity, so in a nutshell, what does it mean? It simply means that the eddy processes do not influence significantly when PR is small, because this quantity here is much, much larger than that quantity. Or in a nutshell, in simple terms, if we cancel those rho Cp, then we are just saying much greater than eta. And so if you draw the profile, again, we will have our sublayer, lamina, we have our buffer region, and we have our turbulent region. So in this particular case now, what are we saying? We are saying that the thermal conductivity is very large, very large. So it's almost like it's unchanged. That is for temperature profile. And of course, this will be the velocity profile. So the temperature profile is almost unchanged. Almost unchanged, the temperature profile. So these are very important results which we have gotten using the von Karman's model, where it brings into play the third region, that is the buffer region. And the reason why there is a little bit of problems is the limit which we took in the case of our earlier initial calculations, that the lower limit is sigma b. This is one of the reasons why we have those challenges. Remember, in the Reynolds analogy, we had 0 to L. Now, in the Prandtl-Taylor model, we took our lower limit as sigma b, and there are always challenges with this lower limit. And as we move on, more concepts will come in to try to explain more clearly some of the behaviors in these regions, so that we are able to predict accurately some of the behavior in these turbulent regions, and turbulent regions in the laminar flow regions, buffer region, and maybe there's some region X which we'll come up with, which will even refine some of these equations which we are using to compute some of these things in various systems, whether it is in tubes, or whether we are talking of in cylindrical surfaces, and so forth and so forth. So we'll look at that as time goes by. So let's stop at this particular point. We'll continue with our lectures.